Okay. I had to change the numbers here because you got a negative answer. So I'll do it with the different numbers. It won't match what you got. But if you all got negative answer, that means you probably all did it the same way. So I changed question 1 a little bit. What I did was I said you have a 2.1 ohm resistor, and when it's connected up, you get a 0.18 amp current.
You went to 2.1.
I just said I changed the numbers.
Okay.
Please, it's early and I'm tired. Right, so that's what I changed it to, and then what I did then for the second part was this gets changed to a 1 ohm resistor, and then you will see this increase then to 0.36 amps. So just like what you did, you can make 2 equations. This is an E and an OR. So which equation? It's the E equals I OR plus OR. Isn't that the one? Yeah. So E equals I OR plus OR. And then the second one is E equals I OR plus OR. And then when we solve. So making them equal, we get 0.18, 2.1 plus OR equals 0.36, 1 plus OR. So dividing, that's 2.1 plus OR equals 2 plus 2 OR. So I get OR equals 0.1 ohms. Yeah? Now that's not the same as your answer because I changed the numbers, but are you happy with how I did that? And lastly, to get the E, that's 0.18 times 2.2, if I just put that back in there. Can you just hit that in, please, Monica? What do we get there? .396 volts then. Okay. Now let's have a look at question 2, a more interesting one. Okay, so before I do this, which way is my graph? What do I need on the X and on the Y? Yeah, voltage against current will do. Do I say in the question what I want? No, graph in an appropriate manner. The advantage of putting voltage on the y-axis is we can see the EMF is where it crosses the y-axis, and nicely the slope is minus R. So the I will be first, that is on the x-axis, and the voltage, the potential difference, PDF, no, volts, okay. So the I starts from 0.5 and increases. 0.25. It starts at 0.25, the I? Yeah, it goes up in 0.25, yeah? Until 2.75. And what happens with the voltage? It starts at 1.75 and decreases by 8ths, is it? Until I get down there. Okay. Happy with that? Okay. Let me just alright, so part 1 I didn't do, draw the circuit, but you have the circuit in your notes. So there's nothing special there. B is to make the graph. Okay, so let's graph this. Scatter, next. This is PD, PD against current. X-axis is current in amps, and y-axis is potential difference in volts. Okay, so you all should have gotten a nice enough graph like this. Whoa, let's make this one a bit smaller. A little bit smaller. There we go. Okay, did you all get a similar looking graph? Let me just move this guy out of the way. Just bring him down here. Whoa, no, stop! Okay. Use your graph to get the internal resistance and the EMF. So, oh no, it's doing that thing again. There we go. Insert trend line. Right, what did you get for the EMF?
2.1.
About 2. We'll see exactly here. What about the internal resistance?
1/2.
About half? Okay, good job. Yeah, the internal resistance is minus 0.5 ohms, and the EMF is 2 volts. Okay, let me just save my beautiful picture. Right, next, add in an extra row of load resistance. Now, load resistance is the external resistor connected to the circuit. In this question here, you change it. You know, that's how you got the different values. But now, well, 1 second. Desktop. No. Okay. Right. Let's have a look here. So how can I get the or here? V over I. V over I. Now it's all different. And the reason it's different, you know this because we did the circuit in class. You have the cell, the internal resistor, and this is in the battery pack. And then you have a resistor here, which you're changing. And here is the ammeter. And here is the voltmeter. And this changes. And actually by using the triangle, you can see the different values of or I must have used. Okay, so you're happy with that one then. Now, next, the power. So what's going to happen here is that this resistor is going to get hot. That's why it's using up the voltage. So it actually is, it does have some power here. How can I get the power? You have many choices, V squared over or. Yeah. So power in watts will be this times this. Yeah. Okay. Now, next graph. Make a graph of power against resistance. So make another graph where this is on the X and this is on the Y. Okay, so let's make that graph now. And this graph will be quite interesting in its shape. This is power against resistance, or perhaps to be more precise, the load resistance, the external resistance. And the x-axis is load resistance in ohms, and the y-axis is power in watts. Now, have a look at this graph. Let me put in a line onto this. It's going to be quadratic-y. Polynomial. Polynomial. Let's see what happens. Oh, ugly. That did not work. Maybe it's not polynomial. Maybe it's more exponential shape.
Power.
I want to put in a line. Maybe it's this shape. Whatever. Alright, you can imagine, you can use your eyes to join the dots. So it goes up and then comes back down. Oh no, one more time. I really want the line in there. Can I make it 10? No. Whoa. Never mind. I should have drawn it in when I was picking the sentence. Anyways, the point I'm making is you can see this graph clearly increases and then decreases. That's the point here. So when you look at this graph, there actually is a maximum power. There is a maximum power you can get from this resistor. And when do you get the maximum power? Well, here, when the resistance is 0.5. So when is power maximum? The answer is when the resistance equals 0.5 ohms. But we've seen 0.5 earlier. Yeah, so in other words, when the OR external equals the OR internal, that's when we get the most power. That's the maximum power. Okay, so what is the efficiency here? What's the efficiency of this system? Well, what is the useful output? The output is the power from the resistor here. Okay, so that would be P out over P in times 100. Now, it doesn't have to be power, it could be work. So you could also do work over time and work over time. So work out over work in if you wanted to. Doesn't matter. Right, what is coming in? What is going into this circuit? What's providing all of the power? Well, it's this thing here, isn't it? Yeah, so power will equal IV. And what's the V, did we say here? 2, wasn't it? This was a 2.
Yes.
Yeah, so that's equal to 2I. We don't know the I. Right, what about this guy? What's the power here? This is power in, power out. That's going to be IV. Now, what is the V here? Well, we can get this maybe from our table. If I just move this out of the way. Come on. Hey, whoops. Steady now. So this is the maximum here, and at the maximum the voltage through the resistor is 1. So that's I times 1. So using this formula, it would be 1I over 2I times 100, which equals 50%. So in other words, the efficiency must be less than or equal to 50%. So the most efficient this circuit could be is 50%. Finally, this should remind you of something we said in the previous chapter, that efficiency is never 100%. And for this circuit, the most efficient you can get it is 50%. Which means, if you think about it, what I'm saying here is, when you have a battery, it has an internal resistance. The most efficient way to use this battery is if the external resistance is equal to the internal resistance. This is the most efficient way to use the battery. Okay? If your external is bigger than your internal, or even if it's smaller than your internal, then you're using the battery less efficiently and wasting more energy. Okay? So this is quite an interesting question. I saw this in the exam a long time ago, but the good news is in the exam they did it like how I did it, which was they broke it into parts. So they said, now make a graph of power against resistance. From your graph, what is the maximum power? You know, they really gave you the steps here, so it was actually quite manageable question. Whoops, there goes my phone. But don't worry, it's not broken. Okay.
Teacher,
Yeah.
the efficiency can never be 100 watt about superconductor.
Yes, I was going
Yeah.
It's possible for the resistance to be 0. That is true. But I don't know if you can make... Well, you see, it depends on your definition of efficiency. So, the superconductor might seem like 100% efficient, but you have to spend a lot of energy to keep the superconductor on. You know what I mean? It's not like it just is naturally a superconductor and it just sits there. Just like with the example where we were able to make a material have no resistance by keeping it at the super cold temperature. Well, it's not like, oh, we saved so much energy because there's no resistance. You're spending a lot of energy to keep it at this temperature. So, the most efficient things I can think of, there's two things which are high on efficiency. Electric heaters. Because if you think about it, most heat waste is caused by heat.
Oh.
In the case of an electric heater, this is actually what you want. So what is the efficiency of an electric heater? Where is the energy loss? It's nearly 100%, but it's not 100%. So what is the wasted energy in an electric heater?
The wire.
Yeah, but like what form of energy, you know? Like how is it wasted? In what form?
Kinetic.
The heater's not moving.
I mean the electron move from
What?
wire to wire.
That sound. You can hear the heater, it buzzes, and light. It glows. You don't want the heater to have light or sound, you just want it to have heat. Yeah. And the other thing which is highly efficient is LED lights. LED lights are, again, quite high, nearly 100% efficient. Yeah. Oh yeah, LEDs and electric heaters are the two high ones. Okay, next now. Oh wait, let me just save my second graph here. And let me save my table. Okay, last lesson on potential electricity potential divider. No, we'll just finish this and let's see.
Too long.
It's not too long. We'll finish this and then we'll go.
We are getting tired.
Oh, come on. Really? There's only one lesson left, and then once it's finished, you can go.
So there's tons of questions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Goodness sakes, such a bunch of babies.